attendees to hear you. This system.
My apologies. I'm going to repeat the presentation just really quickly. Give me 1 second. Once again, today we'll be covering structural irregularity. Today I'll be covering actual projects, 2 actual projects. The first one is a steel composite eye girder bridge project. It's a rehab construction, and some of the remarks is that this structure has a varying bridge width, and there are additional girders joining. Second project is a pre-stressed concrete eye girder bridge, and some of the remarks is that the girder lies in transverse direction, and parts of girders are not covered with the bridge deck. So the first project, as you can see, has the deck widening in the middle and also gradually throughout the whole structure. You can see further details in the framing plan as shown over here. That's the original structure. And this is the phase 2 through 5. There is a rehab going on, and as you can see, in the phase 2, the left end of the bridge is removed and constructed. And in phase 3, the middle portion is removed and constructed. Phase 4, the end portion is removed and constructed. And in each phase, the lanes are running in different directions. And some of the lanes, such as over here, will have varying direction flow of the traffic. So the key point I want to cover here is that the construction stage was covered multiple times in other training sessions. But today I'll be focusing on how you could actually set up the moving load analysis that are different in each construction stage. So the discussion points for the first project is the manual modeling approach, steel composite wizard. So for this project, this type of irregular project, you could use 2 ways, either model using the wizard, but then the wizard cannot handle varying deck width. So you actually need to combine multiple sets of model and modify from that point on. But the approach that I'll be showing today is importing the CAD file, either MicroStation or AutoCAD, and then modeling portion. The construction stage setup for the rehab project. Basically how to set up rehab projects, and in connection to it, how to set up moving load analysis. That's for the ongoing different phases and the vehicles running in different directions and so on. So the second project is, as you can see over here, the bridge deck is poured through this deck outline. Basically, these are Ohio pre-stress beam sections, wide flange 60 beam, and some of the outer girders B1, B2, B3 actually have smaller sections. So for the significance in this one is that unlike a usual pre-stressed concrete composite structure, this structure has the girders lie in the transverse direction of the to the bridge direction. So I'm going to show how you could actually manage that, this type of irregularity. A little more details about the project. Unit 1 drawing and the second drawing. And the discussion points for the second project is that also the manual modeling, especially when the deck lies in the transverse direction. And here I will try to cover what are the things that you have to be careful when you try to import from the CAD and vice versa. And the stage setup for the non-uniform deck pouring. So the deck isn't really poured for the entire girders in this example. So I'll be covering how to actually manage those type of non-composite portions and setting up, linking it to the construction stage analysis setup. So as you can see, this is the first project example. Give me 1 second. Let me hide the deck portion so we can see clear view of the girders and the joining occurring. So as you can see, in this portion, the girder is joined. And in Midas, you can actually handle that without any problem because it's an FEA program and it's only a matter of drawing additional lines for the joining girders. And the diaphragm is also modeled using the beam element. And to provide a brief overview of the modeling approach, the girders are modeled using frame elements, the beam elements, and the deck portion is modeled using plate element. Details such as weldings or connections are not reflected in this model. It's more of a general analysis approach model. But as you can see with the plate diaphragm, the girder is connected to this beam and going through to the forward direction, just like any other girder lines. Okay. For this type of modeling, there are, as mentioned before, there is a way to use the wizard and modify the model that the wizard creates quite uniformly. And the second way is to import from the CAD. So basically, in the CAD program, you can have different different part of the structure lightened like this. And here, to make your life easier, what you have to do before importing into Midas is you have to put different part of the drawing in different layers. So currently, I have 5 different layers. Bearings, the bracings layer, and the deck outlier outer line layer, and the girder layer, and the transverse element layer. So for different part of the structure, I actually assign them in different layer. So that way, when I import, so in this blank model, I already defined my materials and sections. Steel A36 and steel A572, and the concrete for the deck, and the eye sections for the plate girder, and the rest of the framings and diaphragm sections. So when I go to the main menu, go to import and go to AutoCAD DXF file, here I could bring a DXF file from the into Midas Civil. And here, as I mentioned before, since I assigned different part of the structure into different layer, I could actually import them one by one. And right now, I actually assigned all the girder sections in one girder layer. However, I have multiple different girder sections. So either in CAD or in Midas, you can take your time distinguishing different part of the girder with different sections, or you could actually do the same thing in Midas after just importing them all together as a girder. Okay. So all my girders are just imported, as you can see. And also, I selected my material and section for the girder. So therefore, as I import this line from the CAD that is assigned in girder layer, the girder section is applied at the same time and outlined exactly the way I extracted from the CAD drawing. And then the transverse diaphragms. Also assigning the proper section for that area. I'm referring to the plate that the girder end is attached to. Looking close, now the transverse, the end plates are imported. So this way, one by one, you could actually import different part of the structure like this. So that's how you could easily handle this type of irregular deck whitening or the girder, additional girder lines model like this. Okay, so that way you could import different layers one by one and mesh, auto mesh the deck portion, and finally complete the modeling. And here the stage analysis is already set up in the phase 3. So this model is reflecting the phase 3 and 4 model. In phase 3 removal wet stage, the wet concrete loading is applied to a part of the structure. And in phase 3 dry, the wet concrete is actually activated. And in phase 4 phase 4 construction wet stage, the wet concrete loading is applied, and then the deck is poured for the rest of them. And this type of staging setup is possible because here, let's go over the stage setup one by one. In phase 3, so currently, as you saw, the bridge is kind of cut in half, and the deck is poured in sequence. And in phase 3 removal, wet, as you can see, there are element tab, boundary tab, and loading tab. And in the element tab, you can actually activate a group of node and element. And in this stage, the base framing plan is activated. And this group is actually including all of the steel bare members. And in phase 4 and in phase 3 wet over here, the wet concrete loading is activated for the phase 3 portion of the structure. And in phase 3 dry, the deck is actually activated, and the rail in the end is also activated. In phase 4 construction, the wet stage, nothing much changes in terms of node and element, but the wet concrete loading is activated for the other side of the bridge. And in phase 4 construction, once again, the deck portion and the rail portion for the other half of the structure is activated. And right now, I just walked through how the stagings are composed. So now I just want to walk you through a little more detail about those groupings. So each time in this phase 3 removal wet stage, this part of the structure, I mean the entire the bare framing is activated. And in phase 3 removal wet, the wet concrete is also poured. So different structure group. So this is the element group that we also saw in the construction stage composition window. And the boundary group, I kind of skipped this portion, but this is related to the link and support. And in the loading portion, the wet concrete loading and the hunch loading and also the rail loading are put in different groups. So the stage composition was a matter of when you assign the proper group into the proper stage. So in the phase 3 removal wet staging, the base framing plan, which is also right here, and this group is including all the steel members. And in stage 3 removal dry, the deck portion and the rail is activated. You can also find them over here, the left permanent rail and the left proposed deck. And let me actually show you in the model view. The base framing plan, let me activate this group. Exactly as what we see in the phase 3 wet stage. And the left permanent rail and the left proposed deck portion is the concrete portion for a part of the structure. Like this. In the same way, the right proposed deck and the right permanent rail are also over here. So this way, using different group of structure group that actually contains different group of node and element, you could freely compose a construction stage like this. And that way, this example model isn't actually covering the entire phase and the entire part of the structure, but you could actually simulate this type of staging like this. And the second portion I wanted to cover for the staging and is the moving load, as I mentioned before. So for the moving load, give me 1 second. So the trick to the moving load is actually connected to the construction stage. So right now, as an example, I defined 4 layers total. Okay. So the lane 0, 1, 2, 3, 4, they're all lined in going from this way to that way. And as you remember, the phase 3, in the phase 3, this left portion of the girder is, the deck is poured first. Let me, like this. So in this stage, we only have this example lane 2, 3, 4 available and able to run in this stage. So among the 5 lanes that I defined, lane 3, 4, 5 could be running in the stage phase 3 removal dry. And for cases like this, I created 2 moving load cases. One is for after phase 3, and the second one is for after phase 4. So the phase 3 actually has, okay, give me 1 second. Let me go over my moving load, all the detail first. So for the moving load setup, I went to the load main menu, have chosen the moving load type, selected ASHTO LRFD moving load code, and I define my lanes as you can see over here. The lane, I actually define the lane based on this outer girder line as my reference line to the lane. However, if the girder lane isn't really parallel to the reference line that you initially started with, feel free to define any type of feel free to define an additional line that's going to be parallel to your girder. So that way, right now, if you see my lane 0, for example, it's actually running perpendicular to this reference line that I selected. But let's say the lane 0 actually needs to run more in the vertical direction that I'm drawing. This way. One second. So if the lane needs to run that way, what you could do is you can actually draw a dummy line that's going to be parallel to that lane that's not actually parallel to the girder. So for example, in this case, if you want to draw a lane that's not perpendicular to, let's say, one of the girder line, you could actually draw a dummy line, so that's parallel to your lane locations. Go to Create Element in the Node and Element main menu. Go to Create Element here, choose General Beam or Taper Beam type. I'm going to choose just like a random number for the section in the material property, since I do not really intend to assign any type of property to it. And let's say the lane 0 is running in the direction that I'm currently drawing. Then create a dummy beam like this. So that way, when you compose the lane later on, you're not actually holding this outer girder as your a reference line to the lane, but actually select this dummy line as the reference to the lane that you define later on. But right now, I actually assume the lanes are running parallel to the girder and simplified it. And this lane, you can actually, so right now, and in this example, it says the maximum lane width can be 11 feet. But it can be flexible, it could be reduced, or the vehicle location may vary within the lane. Then when you define the moving load lane, right over here also, and also for this model, the deck is modeled using plate element. So that case, you could also use the traffic surface lanes. For the model that you model the deck portion using plate element, the traffic surface lane it can be more accurate approach. But for this example, I just simply define the line lanes. So when you define your lane, pay attention to this portion. So it's originally grayed out like this, but when you check on this traffic lane optimization, what it's going to do is ask you the lane width and also the lane width. And what's basically happening and why the lane width actually matters with the traffic lane optimization option is when the traffic lane optimization option is checked on, the program will float the wheel locations within the lane. So that way, before, the wheel is assumed to be running in the center of the lane, but now we are actually giving it the choice to float it within the lane. So this way, if the lane width may vary, feel free to use the traffic lane optimization option and define the lane width. So within the lane width, the program could actually float the wheel, the vehicle load. And as you can see, element 500 through a higher number is chosen as my reference line. And as you can see in the model view, it's actually the red highlighted this girder element. like this. And also, if there is any skew to it, you could actually define your skew angle to the traffic lane that you defined. And traffic lane 2, same, but actually with greater offset. So that way I could actually define the lane 2, which is over here, further from the reference line. And pay attention to the moving direction. So if you are actually, so in this example, we have the lane direction decided. Or so by default, the moving load direction is considered to be both. But if you want to be more effective and don't really consider both cases, you could also eliminate the define the lane to be moving in forward direction or backward direction only. So that way you consider only one of the case. But normally, I mean, if the yeah. So this way you could also control the flow, the direction of the traffic flow using the moving direction option. For the vehicle, I simply define my HL93 design and truck and the tendon. But you could also define any type of permit load. So that way, if you need the permit load running, you could use this permit load too. And in the moving load cases, here I composed 2 moving load cases, as I mentioned before. One to run after phase 3, and another one to run after phase 4. In the moving load case for after phase 3, it's actually going to have 3 lanes selected. So remember lane 0, 0 and lane 1 right over here. It's now composite after phase 3. Lane 2 through 4 are the part where the girders are composite. So in that case, for that case, I only selected lane 2 through 4. So choose my minimum number of loaded lane possible to be 0 and maximum number of loaded lane to be 3, and define this. And also define the truck load. So I have 2 vehicles to consider, the tendon and the truck load. And the same lane setup is used as the one before. So the 2 sub-loading cases are assigned within one main moving load case. And the second one is for after phase 4. And for this one, after phase 4, that's where the lane 1 and lane 0 lies. It become composite. So I only have chosen lane 0, 0 and lane 1 to be running in this example. Oh, actually, it's going to be different. So this is what I initially thought, but now actually after phase 4, the entire structure become composite. So this way, on top of lane 0 and 1, I mean 2, 3, 4, lane 0 and 1 will have to be added in addition to what we had already running in phase 3. So change the maximum number of loaded lane to 5 and leave the minimum number to 0. But then again, after phase 4, we have all the lanes can run the traffic. So instead of having just lane 0, 0 and 1, I moved the entire lanes to be considered. And here we have different moving load case, phase 3 and phase 4. Just because we define them, it doesn't mean the program yet knows when to run each moving load case. So for that, you can go to Analysis main menu, go to Construction Stage Analysis Control. And basically, analysis controls are often disregarded in case you're running with in case you're doing like a simpler type of project. But in case you're doing a complex type of project, such as right now, this analysis control functions could be really, really helpful. And as one example, I'll be showing you this one. So in the construction stage analysis control data, you could basically choose. So originally, the analysis control data setup will have the last stage to be the final stage. But right now in this type of project, we have to run moving load in two different conditions. After phase 3, when one side of the deck is composite, and second time will be when the other side is also poured and the bridge is fully composite. So in that case, for the final stage, for the after phase 4 moving load case, where all the lanes are running, you can actually set the staging to end in the last stage. But in case if you want to consider this phase 3 moving load, you want to change your final stage to other stage and choose that stage that you want to run the moving load analysis after. So if I were to fully set up this model, I probably will have two models saved, one for after phase 3 and another one for after phase 4. So for this model, I could actually end the staging in phase 3 and delete my fourth moving load case. And in the other model, I could actually save it as another model and end the final stage. Make the last stage to be the final stage and get rid of the phase 3 moving load case since we no longer need it. We only need to consider the phase 4 moving load case, which considered all 5 lanes. And in the previous model, again, you could end your construction stage after phase 3 and delete the fourth moving load case. The after phase moving load case. But I'll leave it as whole as of now. So this way, different type of vehicle, the traffic lanes, you could actually set it up and use this construction stage analysis control data and change the last stage to where you want to end your moving load. By using this final stage function, the benefit will be you don't have to create multiple model. You could actually you could actually change the final stage. But you could also save it as another model for the phase 3 when the phase 3 is completed and when the phase 4 is completed. Okay, so that was about the first project. And the second project over here. So for this project, I took different modeling analysis approach. So the first one actually had the deck portion modeled using the plates. So when you look into the details of it, the plate portion, let me activate just the plate part so we can have clear view of the deck. So the deck is modeled using the plate. However, in this model, the deck portion is modeled using the beam element too. And for that, in Midas, you could actually use the composite type of section to model the deck portion and the girder portion at once. Okay. So to give you an overview about this model, in stage 1, the girder 1 is casted. So the first set of the girder are casted first. And in girder 2, the second portion is casted. And in stage 3, the first part of the deck is poured. And as you hope you remember, give me 1 second. The deck isn't poured for the entire part of girder 1 set. but it's actually poured partially. And in stage 4, the deck is poured for the other side, but not really for the entire part. So reflecting this condition right here. For this, I actually got the drawing from the consultant. So this was the original drawing, but in order to make it Midas friendly, I had to edit some of the information in this one. So this is the original drawing that I received, and in the modified drawing, I simplified it, but also added an additional component such as these transverse dummy beams. So in the original one, the difference was the deck outlier was modeled using the splines, like combinations of splines and lines. But I actually drew this deck outline using just the pure line element because splines cannot be imported. And also, this represents the intermediate, diaphragm, the pier portion. But since we are going to use the beam element, I actually got rid of the other lines, but only used the center line to model it. So leaving multiple lines to represent, like each section, one. So trim it down to one instead of multiple lines. And for trimming down, it's better to use the center line instead of the outer line. And this girder is kept as they were originally. And this girder, the deck outline portion is drawn again freshly using the line element as mentioned before. And one thing that I added in addition to what that was already in the drawing is this transverse beams. So in the grillage modeling approach, you actually need transverse dummy beams. So when you look at the model, let me turn off the hidden view so we can just take a look at the clear view of the lines. So these are the girder lines. However, as you know, for the grillage analysis approach, both the girder and especially the deck portion is also modeled using the beam element. And beam element is only in one direction, one longitudinal direction. So when the deck is modeled using the beam element, what happens is the transverse, there's nothing that actually represents the deck in the transverse direction. So right now our girders are running in the longitudinal direction. Let me activate a part of it so you could easily visualize what's going on. So for the composite portion, the deck is also modeled using this composite section. And when I activate all, here we go. Right now, what you are seeing is this green beams that are representing the deck in the transverse direction. They are indeed the dummy deck members, and they lie in the transverse direction of the girder in order to provide a transverse stiffness of the deck, which isn't done with the longitudinal members. And for this one too, I imported from the CAD. Give me 1 second. So for this model too, you could import the specific layers that you want. And when you import different layers, the benefit is the different part will be also kept, like the layer setting. So before I had the girder center lines in one layer, and the slab outline was defined in one layer, and the transverse dummy deck beam was also assigned to a different layer. So this type of separation can be also considered when you import from the CAD. And this can be really beneficial when you try to assign different sections. So let me give you an example with the girder portion. So I'm going to define an additional section. First, I'm going to define a girder portion. And as mentioned before, this example has the Ohio wide flange precast beam as an example. So simply by going to the pre-stressed concrete tab and choose the pre-stressed concrete I section, choose the ODOT as the section name, and find the specific section that's already in my civil database. Define this girder section. Give me 1 second. Let me undo this quickly. Okay. And as you can see under my tree menu, WF, the wide flange 60 beam is defined as I click apply. And then now you can go to the composite section tab. And here find the composite I type, which is for pre-stressed concrete I composite section. This is where you can define the deck and the beam together. So define the girder to girder distance. Define the thickness of the deck. Define the hunch height. And for the girder portion, you can actually import the section that's already defined using the database. So this way I could model the composite section really quickly. And in order to consider the different material for the deck and the girder portion, you could actually choose this select material from DB and provide a exact material for the girder and the deck portion. So this way, the program now, when it calculates the section property for before composite and after composite, it knows that the each portion has a different material property. So use this type of modulus, the modular ratio for the girder and the slab portion. Okay. And here what I did is from this point on, I actually took a lot of time trying to define different groups. So as you can see right here, in my completed model, I didn't entirely complete model the thing, but I actually completed model so I could set up my construction stage. So if you look at this example, I define multiple groups for the girder composite and non-composite, but let me show you some of the most representative ones. So I put the abutment 1 in one group, abutment 2 in one group, and going down, I put girder 1 in one group, girder 2 sets in one group, and pier in one group, pier 1-2 in another group. And then I also define the transverse deck in one group and another group. And if you also look at the section, my list of sections, the W flange, the wide flange 60 beam is assigned to the non-composite area. And the 11 is a composite, exactly the same as what I showed before, but composite with the deck portion. So if you look at it in 3D view, the part that I defined just a beam, it's non-composite, and the part that I define with the composite section is actually has the deck running like this. And the part for the second portion 2, composite, the purple lines, and the non-composite. So this way you could distinguish the non-composite portion and the composite portion like this. And how we set it up is when you go to the construction stage, I set up 6 different stages. Girder 1 is first casted, so the first set of girders and the second set of girders are casted, and the deck is actually poured. Actually, for this middle portion, the deck should be casted at once. But when I work around for this, I actually casted them separated. But in reality, they should be casted together. This portion. And in the deck 1 is poured, deck is actually poured for this area, and then the deck is poured for this area. But in the actual construction, the deck pouring is divided in this edge right here, not really this way cutting sharp parallel to the abutment. It's actually poured and casted with this line as a barrier. And the composite short-term stage is also defined, in which the additional component and the wearing loadings are applied. And in the composite long-term state, not much change is made, except the duration is over 10,000 days. So we could actually consider the creep and shrinkage effect. And let me show you the stage setup one by one. The girder 1s are casted. As mentioned before, the upper part of the here should be also casted in this stage, since the girders are running continuous and casted at once. And girder 2, the second portion, which is originally here in the real project, is casted in this stage. And the deck is first poured for the first part, should be up to here actually. And the deck 2 is also poured, should be again from this point, not really cut in this way. And as I mentioned before, the composite and the non-composite sections are defined. And when you actually look at the girder 1 or 2, even the portion that I defined, the composite section, you don't really see the deck portion yet. So for the composite section, in order to distinguish the compositeness for the construction stage, you use this function, composite section for construction stage. The girder 1, so you can actually select the section, composite section, and separate the part 1, the girder, and the part 2, the deck portion, and have them activated in different stage. So the part 1, the girder, is activated and girder 1 casted, the original state where these members are activated. But the deck portion, since the deck is poured later after the girder is casted, you can choose different composite state to be for part 2. And also, this part was covered in the last training session in the post-tension box application example. But the age over here and the H is related to the time dependency of the material, compressive strength, and creep and shrinkage. So I won't go into too much detail since it's already covered. But the age will strictly affect the compressive strength according to the age, and the age will affect the creep and shrinkage calculation. And for this example too, remember for right now our girders are running in the vertical direction, I mean the transverse direction. And the deck isn't really, it's not really geometrically like perpendicular or parallel to the girder, it's neither of the case. So in this case, what you will need to set up the moving load analysis is you will actually need to use this deck outline line Or you could actually draw a dummy beam that could be the reference line to the moving load analysis. So for example, if you want to use this outline as your moving load reference line, you could actually use this outlines. Like this, go to moving load. Use those element ID, define the lane width, and define the eccentricity, and define the lane. And right now my lanes are defined, but there is an error. So the moving load is defined about this outline as the reference line, but if you have an experience with the moving load analysis, this may be a common error that you will encounter. For this type of error, the reason is because when you display your element local axis, it's actually different. It's not exactly the same. So if you look at this one, so if you look at the highlighted portion, do you notice the faint, the green arrow? So the direction is actually uniform throughout the beams. But when you turn on your local axis, the axis direction may not be the same. And also for this type of case, the exact cause of this type of error is the element IDs are not really in the incremental order. So right now, I define my lane to be covering this element IDs. However, the element ID that I inputted over here is in the order of increasing magnitude, but in reality, they're not really put in into continuous incremental order. So for this type of error, when you encounter this type of error, what you have to do is you can actually renumber your element, go to node and element, go to renumber element, and renumber your element like this. Give it the new starting number and refresh. So this way, when you select your lane and copy this element ID, this is now in the order of increasing. Like this. And also, let's say this deck outline isn't really necessarily the reference line that you need. You can nearly draw a new line, create a new element, make sure that you choose just like a dummy material, and also the section that's very, very small and negligible. So the purpose is only to kind of locate the beam, but nothing further. So this way, if your lane is running, not really necessarily strictly following the deck outline, or if you just simply need a new, line, just create a new line that can be the reference line to the new vehicle lanes. And same goes for the previous project too. Okay. This was up to what I wanted to cover today. Let me go over a couple questions and we'll conclude it soon. Okay, one of the question was when importing from the CAD, either AutoCAD, once again MicroStation, is there a setting that defines the fineness of the model, such as node spacing along the girder? So when you import a CAD file, either Station, MicroStation, or AutoCAD, you could actually just so the node will be created where the line disconnects. So for example, in my case, for this example, this line segment is ending in multiple segments. So when you actually just see it, it seems to be ending here and here. But in reality, what I did is I actually disconnect them multiple times. So it's made of multiple segments like this. And when these multiple segments are used, each end of each line segment, that's where the node will be created. So that way you could actually control the fineness of your model, such as node spacing along the girders, the size of the beam, or even the size of the plate when you mesh using the auto mesh feature. And the recording will be sent out to everyone. There were a couple requests. And for the moving load analysis, the wheel load can be can be floated in transverse direction, and but the lane itself will be fixed. However, I actually mentioned this in other trainings. Right now, as the second improvement, you could actually float the lane in the transverse direction. However, but then the lane itself cannot be floated. But what will be changed by the end of December is the moving load, the entire floating, even with the lane, will be available. So that's the third improvement that we're actually bringing to Midas Civil for the second update in this year. So right now, the lane itself is fixed, but the vehicle is floated. But in December, all you need to define is the vehicle width and the vehicle type. The lane width and the vehicle width and the vehicle loading. So that way, the program could actually perform the entire floating. And as the conclusion, thank you for joining me today. For any other question, please contact me at my email, as you can see over here. And please note that this course is not a PDH accredited course. Thank you. Have a nice day. Bye-bye.